If the universe is everything, then how can everything expand into anything else?
What if the universe isn't expanding into nothing, but into something? Something we've only just begun to detect. A recent quantum simulation, analyzed using Microsoft Azure's massive cloud infrastructure, might be challenging everything we thought we knew about cosmology. This breakthrough could finally explain gravitational anomalies that have baffled astronomers for decades, or open the door to an entirely new realm of physics, long relegated to the fringes of theoretical speculation. The Azure simulation that sparked it all. A team of astrophysicists used Microsoft Azure to run a quantum-level simulation focused on boundary behavior at the edge of space-time. Unlike standard cosmological models, this simulation aimed to probe the limits of the observable universe and what might lie beyond. Built using cutting-edge mathematical extrapolations from quantum gravity and cosmic inflation theory, the simulation sought to better understand cosmic acceleration, the mysterious force causing galaxies to speed away from one another. Scientists hope to find patterns or signals that could clarify the nature of this acceleration, whether it would eventually stop, reverse, or intensify.
It's a detective story. You have some anomalies, some things that don't quite match what you expected, and you're trying to find an explanation.
Anomalous energy drag at the edge of space-time. But what they discovered was wholly unexpected. A subtle but persistent energy drag occurring as virtual particles approached the model's outer boundary. This resistance didn't align with known phenomena like vacuum energy or quantum fluctuations. Instead, the simulation hinted at interaction with a higher dimensional field, suggesting our universe isn't freely expanding into an empty void, but rather expanding against or through something with physical properties. This was the first mathematical indication of what theorists call bulk resistance, a concept found only in speculative higher dimensional models.
Dark matter is massive, it has gravity, but it's invisible. It has no interactions with light.
From dark energy to dimensional discovery, the original goal of the simulation was to study the behavior of dark energy, the force behind accelerated expansion. The researchers combined data from space telescopes, gravitational wave detectors, and particle accelerators into a model of the entire observable universe with quantum-level precision. But simulating such a vast and detailed structure requires enormous processing power, far beyond any individual research institution. That's where Microsoft Azure came in, handling over 50 petabytes of data in a large-scale run that revealed gravitational anomalies at the model's boundaries. Resistance from beyond the simulation. No matter how many times the simulation was run, or how the parameters were tweaked, the anomalies persisted. Adjustments to quantum interpretations or modifications to general relativity failed to resolve the inconsistencies. The lead researcher, Dr. Emily Chen, described the effect as like watching waves crash into an invisible shoreline. The math suggested the universe wasn't expanding into emptiness, but into something with measurable properties, something that influences our own space-time. Enter Lisa Randall, Brane Cosmology. Revisited Harvard theoretical physicist Dr. Lisa Randall, known for her pioneering work on higher dimensional physics, was called in to review the findings. She immediately recognized the patterns. "What you're seeing," she said during a video call with the team, "matches exactly what we would expect if our universe were embedded in a higher dimensional bulk space." Randall's brane world theory, developed 2 decades ago, suggests our universe might be a 4-dimensional membrane, or brane, floating in a higher dimensional bulk. In this model, gravity can leak into extra dimensions, explaining why it's so weak compared to other fundamental forces. Brane friction and multiversal interaction. One potential explanation: brane friction. an interaction between our universe and a neighboring one. We might be detecting gravitational friction between universes, explained Dr. Sophia Patel, a quantum cosmologist involved in the project. It's like our cosmos is rubbing against another. These interactions could explain localized gravitational anomalies we currently attribute to dark matter. Perhaps, Patel suggested, some of that gravitational influence isn't coming from our universe at all, but from shadow matter in an adjacent brane. Rethinking the beginning and the end. If our universe is embedded in a higher dimensional system, the Big Bang may not have been the beginning of everything, just the start of our local dimensional expansion. It could have been triggered by a collision between branes, or even an engineered event within the multiverse. Likewise, the feared heat death of the universe may not be the end. It could be a transitional phase, as our brain merges with or folds back into a larger cosmic structure. Are we in a simulation with code-like boundaries? Philosophers and physicists are now asking even deeper questions. Is our universe embedded in a computational space? Are the laws of physics emergent properties of a deeper mathematical reality? Dr. Liu pointed out something intriguing while analyzing the boundary behaviors in the simulation. These behaviors exhibited what scientists term computational cutoffs, areas where calculations simplified dramatically, as if optimized by an underlying algorithm. Azure's advanced machine learning models detected recursive mathematical structures that seemed more aligned with data compression techniques than traditional physics. The quantum field equations at these edge cases simplified into patterns resembling error correction codes, typically used in quantum computing to maintain coherence and system integrity. It's as if reality itself becomes more efficient at the boundaries, Dr. Liu noted. Physical processes that require complex calculations in the middle of the universe suddenly adhere to much simpler rules at the edges. This is precisely what you'd expect if computational resources are conserved in a simulation. Is the universe expanding into a processing field? If the universe is indeed expanding into something, could it be the edges of a processing field? What if our perceived physical constants are actually variables constrained by the resources available in a higher reality? This raises fascinating possibilities about the nature of light speed, quantum state collapse, and Planck units. If the laws of physics are the resolution limits of the system generating our reality, then everything we know may be governed by computational constraints. The implications are staggering. This doesn't necessarily imply we're living in a simulation created by an advanced civilization. Rather, it suggests that computational aspects might be intrinsic to reality itself. Mathematical Universe Hypothesis. Gainsground, Professor Max Tegmark of MIT, has long proposed that the universe is fundamentally a mathematical structure. The findings from Azure provide unexpected support for this mathematical universe hypothesis, as they reveal that the universe's behavior at the boundaries of expansion aligns more with mathematical equations than with traditional physical systems. During the final simulations, Azure's AI flagged a critical failure point, a zone in the model where space could no longer expand. Initially, the team assumed they had hit a processing limit, believing they had reached the ceiling of Azure's capabilities. However, it wasn't a hardware limitation. No matter how they reconfigured their simulations or enhanced computational resources, the same boundary persisted. Not due to gravitational or temporal forces, but because the underlying simulation returned a null value. Reaching the edge of cosmic understanding. As Dr. Chen articulated, it's like finding the edge of a map, not just any map, but the map of reality itself. This situation led to the hypothesis that the universe might be pressing up against the outer boundary of its rendering space. Beyond certain coordinates, the mathematics simply could not resolve, as if the physics engine ceased to exist at that point. This finding is particularly striking because it appeared at a specific distance from any observer point in the simulation, roughly 16.8 billion light-years. This distance is suspiciously close to our current estimate of the observable universe's radius, about 46.5 billion light-years, when accounting for cosmic expansion. Asymptotic behavior and cosmic firewalls. The team's attempts to model continued expansion toward this boundary revealed that the expansion itself began to slow asymptotically, never quite reaching the edge, but approaching it increasingly slowly. One team member noted in the research notes, "It's as if the universe knows it can't cross that boundary," suggesting a built-in safeguard preventing anything from reaching whatever lies beyond. This observation has led researchers to propose the existence of a cosmic firewall, a barrier separating our reality from something else. Whether this firewall is a natural phenomenon or engineered remains an open question, but its mathematical signature appears consistent across multiple simulation runs. What if the universe is part of a larger system? If Microsoft Azure has confirmed that the universe is either expanding into another dimension or the edge of a simulation, it fundamentally alters our understanding of cosmic history and the future. This revelation forces us to reconsider terms like universe, reality, and even existence. The simulation isn't merely an abstraction. It provides a model that helps decode the hidden structure of reality. This reality appears nested within something larger, something our current physics cannot fully explain. While this doesn't invalidate the principles we've learned about physics within our universe, general relativity accurately describes gravity at large scales, and quantum mechanics correctly predicts particle behavior. Both theories might be special cases of a more comprehensive framework encompassing extra dimensions and cross-brain interactions. Philosophical questions arise. This realization raises profound philosophical questions about our place in the cosmic hierarchy. If our universe is one of many, potentially infinite universes, then everything that can happen might be occurring somewhere in the multiverse. Every conceivable configuration of matter and energy could exist in some universe, enriching and complicating the totality of reality beyond what we ever imagined. Dr. Randall articulated this sentiment beautifully. We've spent centuries looking up at the stars and wondering what's out there. Now we need to look at the fabric of space itself and ask what's beyond that. What lies ahead in our exploration? If this discovery alters your perception of the universe, you won't want to miss what's coming next. Subscribe and activate notifications to ensure you stay updated because, in the next video, we'll explore the new theory suggesting that black holes might serve as access points to this larger space. Recent gravitational wave data hints at something peculiar happening at the event horizon of black holes, potentially our first direct evidence of cross-dimensional transport. Some theorists propose that black holes might not merely compress matter to infinite density. Instead, they could be puncturing through our brain into a higher dimensional bulk space. This idea might clarify the information paradox that has puzzled physicists for decades. The information lost in black holes may not disappear. It could be transferred to another dimensional realm. If true, the apparent evaporation of black holes through Hawking radiation might represent a two-way exchange of information between our universe and whatever lies beyond. Conclusion: we might be witnessing the cosmic equivalent of quantum entanglement, but between entire universes rather than individual particles. Until next time, keep looking up and out because the universe is stranger and more wonderful than we ever imagined, and we are just beginning to decode its deepest secrets.